Hello, I'm Matt Venn, Chief Sales Officer for Yosis HQ, and today I'm pleased to be presenting Formal Verification Adoption Made Easy, which is a presentation for DVWorld Online. Let's get started. So our topics for today are who is Yosis HQ, what is SBY, a quick demonstration, and then looking at how we can use formal verification with a GitHub action. Running that on every time we push to a repository, and then taking a look at the limitations and how we can work around them with the TabiCAD suite, and finally where to get more information and a free evaluation license. So Yosis HQ is the place for open source EDA. We've been running for about 4 years now, and we're the home of the creators and maintainers of Yosis and NextPNR and related tools. And if you've ever used any of the open source ASIC flows, then Yosis is the part that is doing the synthesis. One thing that people know less about is that we also have formal verification tools, and our open source tools are free for you to get started with. And I'll tell you a little bit more about the limitations and how we can work around those limitations with our paid for offering later on in the presentation. So our mission is to increase access to state-of-the-art EDA, and we're very competitively priced, starting at just €500 per month. If you want to integrate our tools into your tools and pay for support, that's something that we do regularly. And also if you want to pay for new features to be added to our tools. So SBY is our formal verification tool. It's a front end for Yosis, and it's called Symbiosis, shortened to SBY. And I'll be linking the documentation later. It mostly works as a command line tool. We don't have much in the way of a graphical user interface, and we support cover properties, bounded model checks, and K-induction. So just putting on my ASIC hat for a moment, one of the things that formal verification is great for is to make sure that these bigger, more expensive projects that you can't afford to go wrong are going to be working properly all the time. So Tiny Tapeout is a project I started a couple of years ago, and the idea is making a multi-project chip. So we slice up one chip into 500 designs, we support digital mixed signal, and every design is power gated to make sure that if something goes wrong with one design, it doesn't take out the others. All the designs are put inside this multiplexer, and so the multiplexer is a key part of the chip infrastructure, because if anything goes wrong with a multiplexer, that will write the whole chip off. So it's an educational project, and we've been working with many students in universities around the world, and it's really important that as an educational project, it's got to work first time. We can't do a tape out with a bunch of students and then something goes wrong with the infrastructure and the whole chip is a write-off, including all of those student designs. So alongside functional verification, we also use formal verification to check everything is working. And I'm just going to take you through one of the formal checks, which is the connectivity check. And this is proving that all the inputs and the outputs go through the mux and end up at each of those little tile positions. And there's never going to be any wires broken or any missing connections. So the way we do that is that for every tiny tile inside, we assert that the input has got to be equal to the output. And then outside of the chip, we loop back the output to the input. We let the solver drive the output. So those signals propagate through the multiplexer, get looped back, arrive at the input, and then we assert the inputs of the outputs. And we also have bidirectional pins here, and those are handled in a very similar way down here. So if you want to check out the source here, you can take a look at this link. But for now, I'll give you a quick demo on the command line. So here's the repository. Inside the formal directory, we've got a bunch of files, and the important one for us is the connectivity SBY file. So this is the config file. Mode prove is going to first run a bounded model check and then K-induction up to 10 clock cycles. We read in all the Verilog files. Because the design uses tri-states, we flatten them to logic gates. And then here's a list of all the files as well. Those assertions I already showed you here. So they are part of this test design. So to run the tool on the command line, it's just as simple as giving the name of the tool alongside the configuration file. And there's quite a lot of source here because there's 500 different individual files that are all being instantiated. So I'll speed up this footage a little bit. And then we see the base case starting and the induction starting. And then finally we get a pass for a successful proof by K induction. So it's very convenient to be able to run it from the command line, and that also makes it very easy to integrate into a continuous integration system. And that's the bit that I want to show you next, and that I think is one of the things that makes our tool so easy to get started with, because you can just integrate it into a continuous integration system. So we have a GitHub action. And if you're not familiar with GitHub Actions, they are a service offered by GitHub. You have very similar things for GitLab as well as other CI tools. And here we're just saying every time we push or do a pull request or manually request it, we can run this job. There's one job called formal. It's going to use Ubuntu. The first thing it's got to do is check out the repository, and then it's going to install the OSS CAD suite. And the OSS CAD suite is a special set of tools from Yosis HQ. I can show you that quickly now, where we have a big selection of tools. You can see them all listed here. And that includes the SBY formal verification tool. And we have already released over 1,600 versions of this. A daily build and release. And one of the bits that we offer there is a special GitHub action called Setup OSS CAD Suite, which makes it very easy to get that installed into the VM that is spun up when we do this push. I just run a single command here to check the version of Yosis, and then this part here is actually where we run the formal proof. So as you see, it's just the same commands that I ran on the command line, change to the formal directory, and then run SBY. And that file just needs to be inside a directory called .github workflows and then formal.yaml. So here's the same file. I just copied and pasted it. And then when I do a git push or a run from the command line or a run from the GitHub, that action is run, and I can see the logs here. So setup, checkout, install the CAD suite, run the version, so we get to see what version of Yosis is in use. Then the logs for the formal connectivity, so this is the same logs that you've just seen on the command line, with a finished successful proof, and then the job completed. And that was all done in just 60 seconds. So we see here in 60 seconds. So for a simple proof, it can be a very quick win to add this to your system. But let's just make sure it's working. So we'll break it and then I'll push it. We can check that the GitHub action runs and check that that fails. So back in formal. I'm going to edit the file that does the loop back, and instead of looping it back exactly, I'm going to force one line to always be 0. So this would be as if one line of the mux was somehow damaged in the chip. So now I can do SBY TT connectivity.SBY to start running that again, and at the same time I will add that change, break it, and then push it. So back on our GitHub, we see a new job has just been started. Installing the OSS CAD suite. Back on the command line, we see a BMC has failed. So the command line tools locally have successfully spotted that problem. And the GitHub action also fails. So hopefully that gives you some inspiration to see just how easy it is to get started with the Yosis HQ formal verification tools running on the command line and in continuous integration. So what limitations are there? Well, the main limitation that you have with the open source version is that we only support immediate assertions, not system Verilog assertions. And we also only support a subset of system Verilog, not the whole thing. But with the paid version, you get a industry standard system Verilog parser and also system Verilog assertions. So the full details are here on this slide. And of course, one of the things you get with the paid license is customer service. So that wraps up my presentation. Let's just take a look at some final resources for you. We've got the documents for SBY here. So you can get started with SBY, take a look at the reference manual and get started. If you want an evaluation license, you can request one on our contact form. For pricing, if you're a freelancer, it starts from just 500 euros per month, otherwise 800 euros. And that's for as many users as you want running on a single machine up to 32 cores. To experiment with the pricing, we have this handy pricing calculator here. You can experiment there. To stay in touch with us and attend the Yosis user groups, join our newsletter. And also just to let you know that we're hiring. So if you're a synthesis or formal verification person, or you could help us out as a chief operating officer, then we'd love to hear from you. So thanks very much for the invitation to present at DVWorld, and I hope that you learned something about how easy it is to get started with formal verification.